Alright, so we're about to finish off the whole thermodynamics section, and so we're going to talk about Le Chatelier's principle. I always like to talk about Le Chatelier a little bit, since the guy got a principle named after him. If it's not clear, he's French, just to make that is a French name, including the you can tell because it's a French hat on the A. That's a French military hat right there. Um, so he was actually kind of more of an accountant than a chemist. This is the truth. Like, people were kind of, there were people that just used pitchforks and moved poop around to grow cabbage in Europe at the time, and then there were people that kind of just did everything. And so, if you were a scientist, you weren't a scientist. You were a gentleman, and you had other duties. And his main duty was actually he was a glorified accountant, and it actually really comes into play with this process. And we'll talk about that. But he was in charge of the armory in Napoleon's France. And if you don't know your history, I'll just say this: Napoleon's France used its armory a lot. We'll leave it at that. He was a warring fellow. Europe was unstable at the time. And so this idea of, how many cannonballs are there? Well, we sent this many out with the Fourth Army, and now we had this many, and that was his job. It was just like, how many muskets, how many of this, how much of that. And I mean, there was a lot accomplished by these groups. Don't get me wrong. Canned food was invented by Napoleon's army. A lot of people might not be aware of that. I don't know. It was jarred. But that was the first canned food. He's like, how do I? He was all about supply lines, which is ironic when you consider how it ended. He went into Russia too far, and his supply lines deteriorated. But he's like, what do we do? What do we do? Well, we can't always forage for food. What do we do? So you have canned food with a shelf life. So you no longer have to worry about your meat spoiling or whatever. You can just eat it out of a can. Which again, they hadn't mastered cans yet, so it was still glass. So it was heavy. Everything was pulled by horse. It wasn't perfect, but you can't let perfect be the enemy of good. And I'll say that they definitely didn't do that with their canned food. I'm sure it wasn't up to normal French culinary standards either. But you got to do what you got to do when you're out musketeering in the blue. That was their slogan. It was in English, which seems weird, I know, but that was their military slogan. So he was an accountant, and that actually gave him a really good background to think about equilibrium systems. And so he has this principle. So he did do chemical studies as well, but he mostly was an accountant. That's my story, and I'm sticking to it. So here's this principle. If a system, I'm not going to do a French accent when I do this, I swear, I'm not going to do a French accent while I read this. If a system in equilibrium is disturbed, the system will shift back to its equilibrium position. We're going to break this down if this language isn't making sense. And I kind of talked about it a little bit at the end of the last video, so hopefully you're primed for it. But basically, if something's at equilibrium and you mess with it, you push it off equilibrium, it just comes back. No matter what you do, it comes back. It comes back to the equilibrium position. But how does it do that? Well, let's give an example. And this is, hopefully you're starting to see how this is accounting related. Or if not, you will soon. So, if you have a system at equilibrium and then you add reactants to it, so everything's all nice and settled in, it's all cozy at equilibrium, and then you pour more reactants in it, it's going to shift. It's going to have too many reactants. That's what we're saying. So adding reactants to a system at equilibrium, well, that's going to overload the reactant side. That's what we're saying. We're overloading reactants. We're filling up one side of the equation. The other side now is deficient. Well, what happens? It produces more products and compensates. So, overloading reactants, well, that will cause more products to form, which is also going to use reactants up. So it's going to drop the reactant side and raise the product side until equilibrium is reachieved or reestablished. So it's going to cause more products to form until equilibrium is reestablished. That's what we're saying. So, let's play around with this idea. Let's put up an equilibrium system and let's poke it. Let's perturb it. Let's push it off equilibrium and talk about what it would do. So I'm going to use something that is very important biologically. We've got lactic acid. We've got bicarbonate. And we're going to have an equilibrium process, so I draw my equilibrium arrows, and I get lactate, and carbonic acid. Just fit it on the page. Alright. So over here, we call these reactants still, even though they're reactants for the forward reaction, we let that kind of decide our whole perspective. They're products on the reverse reaction, but whatever. We don't worry about it. This is how it's written. So it's just like a normal chemical reaction. We go reactants and products. Alright. Uptown, downtown, you know. We're just drawing a line here. So to the left of equilibrium arrow, we call these reactants. We can also call this left and this right. Hopefully it's clear why we might do that. So either of those are fair game. So when we mess with a system at equilibrium, it shifts left or right. It shifts towards products or reactants to compensate. So let me ask you a question. What could we do to shift, to cause equilibrium to shift right towards products? What could we do? How could we do that? So think about what we talked about before. There's kind of two general things we can do, or you can talk about it in four very specific ways. So if we want to cause it to shift right, well, we can add more stuff. We can add more reactants, and then it's going to have to shift right to compensate, because now this side's overloaded, so it's got to shift right. It's got to make more products to compensate. Or we remove products, and then it has to make more and replace them because we've taken it away. So it has to re-achieve balance. So it's at balance, and we can do a couple tricks, or that's what we do. So, one, we can remove reactants, and it could be just one or both. So we could take lactic, oh, sorry, I have that backwards. Add reactants. So we could add lactic acid. That's going to cause it to shift right. If we could add bicarbonate. That's going to cause it to shift right. Or two, we can remove products. So we add reactants or remove one or more products. And so if we take away some lactate, somehow, maybe we do another reaction with lactate or something, or we can, sometimes you can actually scoop stuff out or whatever. Or we take out carbonic acid, it's going to shift right. It's going to replace those missing things. Now, how would we cause it to shift left? How would we cause it to shift towards reactants? We just do the opposite. So if we want to cause a shift to reactants, well, we can add products, we can overload a side and it will shift away from it, or we can remove from the reactant side and it will shift towards it. So you can pull something right by removing, or you can push it right by adding to the left-hand side. And you can pull something left by removing reactants, or you can push it left by adding products, which are going to make more reactants for it. So it's the same trick. It's just which way do you want to push it, and you just pay attention to what you do. So, hopefully that's making sense. But that's what we mean by shift left, shift right, or shift towards products, shift towards reactants. And that's what Le Chatelier's principle is all about. And hopefully you can see how it's tied into accounting now, because it's like, oh, well, if I take away some bicarbonate ion, then we're going to have to use some lactate and some carbonic acid to replace it. And then lactic acid will go up as well. So it's going to shift right and compensate. So we're going to lose stuff over here, and we're going to gain stuff over here. So it's going to shift left, I should say, to compensate. Just killing it on this video. It was a long section. Alright, so another example, I mean, there's lots of equilibrium things you can talk about. Kind of a broader scale one I always like to mention is diet and exercise. Some of us know this better than others. So, if you have kind of like your body mass is sort of like an equilibrium. And there's sort of two factors that you can make it go up or you can make it go down. And so to make it go up, in general, we're not going to assume you're adding good mass here. We'll assume you're, because you're like, oh, you just lift a bunch of weights. Yeah, okay, yeah. Get out of my video. You can do this by increasing calories, or you can decrease exercise. If you're like, I just want to bulk up, I want to be I'm feeling too thin. What do I do? That used to be a thing, by the way. I mean, so beauty standards have shifted over time. You can look this up, and like there were iron supplements for people in I want to say the 20s. It was like, yeah, the fella is not looking at you. You're too skinny. Have some of our flaky iron, and then the men will be on you like flies, honey. Like, that's a real thing. Like, you can look that up. That's real. And they'd have it for guys, too. Like, oh, yeah, scrawny little fella. You not feel like a proper man. Do you get thrown around like a wet towel when you're at the old tavern? Have some of our flaky iron, and you'll be a beefcake in no time. Like, I don't know if they had that term back then, but, I mean, it's true. So it was like, don't be too skinny. You just can't win. Society just moves the markers. Like, as soon as a bunch of people are something, that something becomes bad, I'm pretty sure. Alright, so you can increase calories, you can decrease exercise. What did I write? Exercise. Thanks for pointing that out, everybody. Alright, or if you want to lower your body mass, you can drop your calories responsibly. You can increase your exercise, which is always irresponsible, in my opinion. Just kidding. Whatever. Go run 20 miles. Be an ultramarathoner. You do you. But our body mass is sort of at an equilibrium between these two factors. That's one example. There's lots of them, but this is the one I always like to talk about. Near and dear to my heart, I've definitely moved this equilibrium around several times in my life. Sometimes you can add good body mass. I've done that. I've also, that was more in my early 20s, teenage years I did that. I've just added other kinds of body mass since then, mostly. Alright, so that does it for this section. Huge ideas in here. Huge. Massive parts of chemistry. I'm not kidding. It's like a crown jewel. If you don't get it right away, don't freak out. It's a big, big idea. Equilibrium is massive. And normally I talk about kinetics before I talk about equilibrium, but that's just not how this class is laid out. So there's going to be some equilibrium stuff in the next section, and so that might help you out here. So if it's not totally clicking, check out kinetics and then come back to this. And I'll try to piece some equilibrium stuff into kinetics as well to help out with that. But there's just some ideas in terms of the speed of reactions, their reaction rates. That's what we're going to talk about next. That really do play into equilibrium very strongly. And I've sort of tiptoed around them when normally I just go full bore. Like, that is my explanation, involves that stuff. But I can't throw it out right now because I haven't talked about it yet. So, just hang in there. Otherwise, ask questions, talk to each other, talk to me, whatever's working for you. You've been in the class a while now, but this is a tricky one, and I am more than happy to help. I love talking about equilibrium. So, otherwise, it's on to the next one.